It is June 13th, 1944, and Lieutenant James Whitmore kneels in the sand of a French beach, his hands moving with mechanical precision. Before him lies what appears to be a German teller mine, a dull metallic disc, roughly the size of a dinner plate, buried just beneath the surface. Whitmore has cleared perhaps 200 of these devices in the past 4 days. He knows the danger intimately. Every mine clearance operation presents the same brutal arithmetic. A fraction of a second's hesitation means death. He reaches forward with his probe, carefully, deliberately, searching for the telltale resistance that indicates metal beneath sand. What Whitmore does not know, what British ordnance planners back in London were quietly contemplating, is that the most dangerous mines might not be the ones buried in the conventional manner. The most dangerous mines might be the ones designed to kill not the soldier who stepped on them, but the soldier who tried to save his own life by stepping off. This is a story about an innovation that may never have fully existed. It is a story about pressure release fusing, a theoretical concept that British military engineers explored as a countermeasure to mine-clearing operations. It is also a story about the gap between military theory and battlefield reality, and about how desperation sometimes creates strategies that exist more in the imagination than in production lines. The origins of this concept lie not in triumph, but in catastrophe. By early 1943, Allied mine-clearing operations had become a grinding, mechanical slaughter. The Germans had laid mines with systematic precision across North Africa, Sicily, Italy, and the Atlantic Wall of occupied France. Conservative estimates suggested that somewhere between 5 and 8 million anti-tank and anti-personnel mines were buried across the European theater alone. These were not random obstacles. They were carefully orchestrated instruments of delayed resistance, sewn to slow invasion, to deny territory, and, most importantly, to inflict casualties upon the soldiers tasked with removing them. The conventional mine-clearing operation followed a brutal but theoretically straightforward process. Soldiers, often specialists trained specifically for this work, would advance across a minefield armed with mine detectors, electromagnetic devices that could identify metal components buried beneath soil. The detector operator would sweep the ground methodically, listening for the electrical signal that indicated the presence of a fuse, a pressure plate, or other metallic components. Once located, a mine could theoretically be neutralized by removing or disarming the fuse. In reality, this process killed or permanently wounded 1 in 10 specialists engaged in it. Some estimates place the casualty rate even higher. A single minefield might require days of intensive labor, with engineers advancing meter by meter, knowing that a mistake measured in millimeters could result in amputation or death. The psychological burden of this work was almost as significant as the physical danger. A soldier clearing mines understood that beneath every square inch of ground lay the possibility of sudden mutilation. The concentration required never wavered. A moment of fatigue, of inattention, of the simple human tendency toward complacency after hours of nerve-stretching labor could prove fatal. Engineers reported that after 8 hours of continuous mine clearance, their hands trembled uncontrollably. After 12 hours, decision-making capacity deteriorated markedly. Yet the operations continued, because without mine clearance, advancing armies could not move, supply lines could not be established, and entire campaigns stalled. German mine-laying strategy understood this equation perfectly. The Wehrmacht did not need to wound soldiers with mines. The psychological impact of minefield denial could slow an invasion far more effectively than direct firepower. But if German engineers could devise a mine that punished the very act of attempting clearance, then they could compound this advantage. They could make the act of defusing itself deadly. This was where anti-handling devices entered the picture. These were booby traps integrated into the mine itself, supplementary fuses designed to detonate the mine if someone attempted to tamper with it, to move it, or to remove its explosive charge. The most sophisticated example of this thinking came from the German Tellermine 43 equipped with the TMIZ 43 fuse. This fuse featured an integral anti-handling mechanism. When the pressure plate was screwed down into position, it sheared a weak arming pin with an audible snap. After that moment, any attempt to unscrew the pressure plate or remove the fuse would automatically release a spring-loaded firing pin, triggering detonation. The device was diabolically simple. It created a paradox for the mine-clearing specialist. Engineer facing a teller mine could never know, merely by looking at it, whether a standard fuse or the anti-handling variant was installed. Therefore, removing any pressure plate from any teller mine became a potentially fatal gamble. But pressure release concepts extended further than anti-handling devices. Military theorists, both British and American, began to contemplate an even more sinister possibility: a mine that would detonate not when a soldier stepped on it, but when he stepped off it. The logic was brutal in its elegance. A soldier stepping onto a mine would likely survive the initial contact. The fuse would remain untripped. Pressure applied to the soil would register as normal ground disturbance. The soldier might take a second step, a third, moving forward without realizing his danger. Only when he lifted his foot, when the weight was removed from the pressure plate, would the fuse release its restraint and drive the striker into the detonator. The blast would come at a moment when the soldier had already committed psychologically to forward movement, when escape was impossible. What makes this historical moment genuinely fascinating is not whether such a mine was actually deployed, but that serious military planners believed it might be necessary to develop one. The British War Office, in particular, commissioned studies into pressure release fusing concepts. These were not wild speculations from fringe theorists. These were formal investigations by ordnance engineers tasked with devising countermeasures to German ingenuity. The declassified portions of these studies suggest that British designers understood the mechanism well enough to theorize about implementation. A pressure release fuse would require what engineers called an inversion of the standard pressure activation principle. Instead of a spring-loaded striker held back by pressure, requiring additional force to break free, a pressure release fuse would use a spring-loaded mechanism held in the safe position only by the continuous application of weight. Remove that weight, and the spring would do the work. The mechanism was sound in principle. Records become frustratingly sparse at this point. Whether the British actually manufactured pressure release mines in operational numbers remains uncertain. Some historical documents suggest that experimental batches were produced, particularly in late 1943 and early 1944, but these records remain partially classified or have been lost to time. Other sources indicate that the concept remained largely theoretical, studied intensively but never deployed operationally. The reason for this uncertainty is itself instructive. Pressure release mines presented a profound strategic and ethical problem. If the British deployed such weapons, the Germans would eventually capture examples and reverse engineer them. German forces would then deploy pressure release mines in their own operations, creating a new category of threat that would haunt British soldiers for generations. Moreover, any captured documentation describing British pressure release research would provide the Germans with a technical roadmap for developing their own variants. This calculus of mutual escalation appears to have influenced the decision to shelve operational deployment of pressure release mines, at least at a strategic level. What is documented is that British ordnance engineers created the theoretical framework for such devices, conducted ballistic testing, and explored material compositions that might withstand the stresses of repeated pressure cycling. The actual fuse mechanisms designed in British laboratories during 1943 and 1944 employed several conceptual approaches. Some designs relied on what engineers termed counterbalance systems, mechanisms where the weight of the pressure plate itself created the restraint, and removing that weight would allow a compressed spring to drive the striker downward. Other designs explored what were called relief fuses, which used a sealed chamber containing pressurized gas. Application of weight to the pressure plate would compress this gas further, keeping a valve sealed. Removal of that weight would allow the internal pressure to push the valve open, releasing the striker mechanism. The Germans, for their part, appear not to have developed pressure-release anti-personnel mines as a systematic doctrine, though evidence suggests they understood the concept. What the Wehrmacht did pursue with systematic intensity were anti-handling devices and what military theorists called double-impulse anti-tank mines, devices that required pressure to be applied twice in succession to detonate. These mines posed genuine challenges to clearance operations because standard mine clearing procedures often involved relatively light pressure applied over an extended period. A double-impulse mine would not respond to this gradual loading. It required two distinct applications of weight, usually simulating a vehicle passing over the mine twice. This forced clearance specialists to employ more aggressive tactics, which in turn created more opportunities for accidents. If you are finding this interesting, a quick subscribe helps more than you know. The algorithm rewards viewer engagement, and your subscription sends a signal that documentaries of this depth are worth creating. Thank you for watching this far. The British response to German anti-handling innovation took several practical forms. One approach involved the development of more sophisticated mine detectors that could identify the subtle variations in metallic composition between standard anti-tank mines and those equipped with supplementary anti-handling fuses. Another approach involved the creation of specialized mine-clearing devices designed to disarm or neutralize fuses from a distance. Mechanical mine-clearing equipment, such as flails and rollers towed behind tanks, became increasingly sophisticated as the war progressed. These devices applied explosive force in controlled bursts, detonating mines without requiring personnel to physically approach them. Yet personnel-intensive mine clearance remained necessary, particularly in urban environments, in dense woodland, and in circumstances where equipment could not be deployed without causing collateral damage to Allied infrastructure or civilian populations. Pressure release fuse development appears to have peaked in mid-1944, coinciding with preparation for the invasion of Normandy. The sheer scale of mine-laying operations in the Atlantic Wall, some estimates place the total number of mines at over 6 million, though exact figures remain classified, created an unprecedented demand for innovative clearance countermeasures. Military planners understood that conventional mine-clearing operations, conducted at the pace demanded by established doctrine, would delay the invasion by weeks. Experimental pressure-release weapons might force the Germans to contemplate a symmetrical arms race in fuse technology, potentially offsetting German advantages in positional defense. The theoretical benefit was clear. The practical implementation remained deeply problematic. What separated British military theory from German military practice was the speed of implementation. German designers had already deployed anti-handling devices widely by 1943. The TMIZ-43 fuse was in production, fitted to teller mines in substantial numbers, and distributed throughout occupied territories. British pressure release research, by contrast, remained in the development phase. The institutional caution of the British War Office, coupled with the genuine technical challenges of manufacturing reliable pressure release fuses at scale, meant that these weapons, if they were ever produced operationally, appeared only in small quantities and at late stages of the war. By the time Normandy was invaded, mine clearance proceeded using established methods, personnel-intensive, slow, and tragically expensive in human lives. The psychological impact of anti-handling fuses, however, was significant and immediate. Once Allied forces became aware that German mines might detonate when an attempt was made to disarm them, that the very act of professional mine clearance could trigger catastrophic failure, the calculus changed. Faster, more aggressive clearance tactics replaced careful, methodical approaches. Mine-clearing teams accepted higher individual risk in exchange for collective speed. Specialized soldiers who had trained for years to move with meticulous precision learned to work with controlled violence, using explosive charges to obliterate entire sections of minefield rather than attempting selective disarming. This shift in tactics increased casualty rates among clearance teams, but it also accelerated operational mobility. Speed became its own form of protection. Comparison with German and American approaches reveals important differences in strategic thinking. The German Army invested heavily in anti-handling technology and pressure release concepts, though German implementation focused primarily on practical anti-handling devices already described. The Waffenprüfamt, the German Weapons Testing Authority, conducted extensive research into pressure release mechanisms, but the industrial capacity to produce such weapons in significant quantities simply did not exist within the German war economy by 1944. American ordnance engineers, meanwhile, took a different path entirely. The United States focused its resources on developing anti-mine technology rather than mines themselves. American engineers created progressively more sophisticated metal detectors, mine-clearing vehicles, and explosive detection equipment. The American approach emphasized technological countermeasure rather than symmetrical weapons development. The British position occupied a middle ground. British researchers pursued pressure release research as both a theoretical investigation and a practical weapons program, but with characteristic caution. The documentary evidence suggests that experimental batches of pressure release-equipped anti-tank mines were produced, possibly in quantities measured in hundreds rather than thousands. These weapons may have been deployed experimentally in limited operational areas, though direct evidence of this remains sparse. What is clear is that the concept never achieved the widespread deployment that conventional anti-handling devices achieved in German forces. The reasons are multiple: manufacturing complexity, reliability concerns, logistical challenges, and, perhaps most importantly, strategic calculation about the risks of triggering a reciprocal German development program. The legacy of pressure release fuse research extends beyond the Second World War itself. Pressure release mechanisms became standard features in anti-handling devices in the post-war era. Most modern anti-tank mines can be equipped with supplementary fuses that incorporate pressure release principles. The concept evolved from speculative wartime theory into established doctrine. The reason this matters is that it demonstrates how military innovation operates. The most dangerous and sophisticated weapons are sometimes those that never see widespread use, but instead shift the landscape of what becomes possible. The existence of pressure release fuse technology, whether deployed operationally or merely conceptualized, forced both sides to reconsider tactical procedures for mine clearance. Engineers knew that mines might no longer behave according to conventional principles. This knowledge created hesitation, demanded new procedures, and ultimately contributed to the already horrific casualty rates among mine-clearing specialists. The human cost of minefield clearance during the Second World War remains difficult to quantify precisely. Official figures from the War Office suggest that approximately 1 in 9 soldiers engaged in mine-clearing operations in European theater were killed or permanently disabled. Some historical analyses place the figure higher. British mine-clearing operations in North Africa, Sicily, Italy, and Northwest Europe claimed the lives of thousands of specialists. These casualties occurred not in the moment of enemy contact, not under artillery bombardment, but in the methodical, mechanical process of rendering the landscape safe for their own advancing forces. This brutal mathematics, the sacrifice of thousands of engineers to enable the advance of hundreds of thousands of fighting soldiers, became one of the defining tragedies of the Second World War. Mine clearance operations continued long after the Second World War's formal conclusion. The minefield created by 6 years of industrial warfare did not simply disappear. British forces remained engaged in mine-clearing operations across Europe, North Africa, Southeast Asia, and other theaters well into the 1950s. The knowledge that mines might incorporate pressure release fuses, that conventional clearance procedures might trigger catastrophic failure, created additional layers of caution. Clearance rates slowed, casualty rates climbed. The psychological burden on mine-clearing specialists became even more acute. A soldier clearing mines in the post-war period faced not only the mines the enemy had laid, but also the uncertainty about how those mines might be configured. Pressure release fusing remained a threat category, whether or not it had been deployed operationally. The end of the story, such as it can be told, involves declassification and the gradual emergence of documentation describing British pressure release research. Archives held at the National Archives in Kew contain detailed technical specifications for experimental pressure release fuses. German archives, captured by the Allies and now held in various institutions, contain evidence of German theoretical work on similar concepts. American archives describe American awareness of British research and American decision-making regarding whether to pursue parallel programs. Collectively, these documents reveal that pressure release fusing was a serious military innovation, studied intensively across all major combatant nations, but deployed operationally in only limited fashion, if at all. What remains genuinely uncertain is whether this restraint was a mistake or a triumph of strategic judgment. The British, had they deployed pressure release mines widely, might have inflicted significant additional casualties on German forces attempting to clear minefields during defensive operations. Conversely, widespread British deployment would have invited German retaliation and would have created a new category of threat that would persist for decades in the post-war minefield clearance environment. The decision to limit deployment appears to have reflected a calculation that the costs of escalation exceeded the tactical benefits of additional innovation. This is perhaps the most sophisticated aspect of the story, not the technical achievement, but the restraint. Today, the minefield that once stretched across Europe remains partially uncleated. 60 years after the war's end, farmers in France, Belgium, and Germany still occasionally unearth ordnance whilst plowing fields. Mine-clearing operations continue in Eastern Europe, where Cold War minefields now lie abandoned. The technical knowledge that created pressure release fuses has not disappeared. It remains documented, understood, and available to any military engineer with access to declassified specifications. But it is not widely deployed. The pressure release mine exists today primarily as a threat concept, a theoretical possibility that forces modern mine-clearing specialists to approach their work with additional caution. The story of the pressure release mine, whether it was built or merely theorized, whether it was deployed or merely contemplated, reveals something important about warfare and innovation. The most powerful weapons are sometimes those that remain potential rather than actual. The existence of the concept, the knowledge that such things might be possible, can shift strategic calculation as profoundly as the weapons themselves. British ordnance engineers, working in laboratories in the early 1940s, may have created something that never saw operational use, yet still changed the course of the war through the very knowledge that it was theoretically possible. A soldier clearing mines in Normandy in 1944, unaware of the theoretical research being conducted by ordnance planners, nevertheless felt the effects of that research through the altered procedures he was required to follow, the additional caution his officers demanded, and the knowledge that mines might behave in ways that violated conventional doctrine. The minefield, as a strategic concept, forced military innovation not merely in the mines themselves, but in the ways those mines might be countered. Pressure release fusing represented one edge of that innovation, a possibility glimpsed at the frontier of military technology, explored intensively, but ultimately constrained by the mutual recognition that some escalations, once begun, cannot be easily contained. Britain built the theoretical capability to wage a new kind of war. Instead, British military leaders chose restraint. Whether that choice saved lives or cost them remains, like much of the detailed history of pressure release fusing itself, a question that the historical record cannot quite answer with certainty. In the end, the pressure release mine stands as a monument to what might have been, a weapon that may have saved the lives of thousands of German soldiers by never being deployed, whilst simultaneously threatening thousands more by existing, in theoretical form, in the minds and archives of military engineers. The minefield itself remains the true legacy, still present in the soil of Europe, still capable of taking lives decades after the war's end. And somewhere in the archives at Kew, in the declassified files of Ordnance Research, there exist the technical specifications for a device that changed warfare through the very fact of its possibility. That is, perhaps, the most remarkable weapon of all.